Hello, I am Francesco Capibollino and I will present Contrastive Learning for Cross-Domain Open-World Recognition. I would like to start talking about a real-world application for our work, an home assistant robot. This is a robot that is designed to help its owner in a number of home tasks. Of course, this robot cannot leave the factory already trained to recognize all the object classes that it will meet during operation. Thus, we want the owner to be able to give instructions to the robot in order to teach it which objects it should recognize by showing how they appear. The robot will later have to be able to locate those objects in a natural home environment. This application involves a number of challenges. First, the generalization from a training visual domain to a very different test one. Then the discrimination of known objects from never seen ones. And last, incremental learning of new classes. So let's start to decompose the problem in all its parts. First, we have to describe the so-called closed word assumption, which is generally adopted by most of the research works that focus on object recognition. The idea is that the categories that will be met at test time are exactly the same on which the model is trained. Of course, this is not the case in real-world problems, so we need to discard this assumption and focus on open set recognition. In this setting, we consider the possibility that at this time we will meet samples belonging to categories that we haven't seen at training time. These samples should not be confused with known objects, and thus they should be marked as unknown. Our task then requires to be able to learn new categories at any point in time, with later predictions which will have to consider all the classes learned till a certain point. We call this problem class incremental learning. By putting together open set recognition and class incremental learning, we are building the open world recognition task. But what happens if test samples come from a different visual domain than the training ones? Of course, we should still be able to recognize them. This is what happens with our home assistant robot, which is instructed by its owner with handheld objects, but later we have to recognize these objects when they are positioned in a natural home environment. So we call this problem domain generalization. We now have all the components of the cross-domain open world recognition task, the one on which we focus in our work. This task has a number of challenges. Our model has to correctly classify samples while discarding unknown ones, but it also has to be able to incrementally learn new classes, and it must do all of this by being domain invariant. Our idea to deal with such a complex task is that we should tackle all its challenges at once. We adopt a single learning objective called supervised contrastive learning. This loss works by organizing training samples on a hyperspherical feature space, where samples of the same class are pushed towards each other and far away from samples of other classes. We model this space by computing some statistics. The class sparsity measures the distance between different classes, while the class compactness tells us how much a single class points are scattered around their center of gravity. We then adopt a really simple incremental learning protocol, which uses a fixed size replay buffer with samples of all the classes, and a class balancing policy in each training mini-batch. Our intuition is that class clusters should be compact and well separated, so we stop each training episode only when we meet this criterion. We then adopt an adaptive threshold to separate known and unknown samples. Indeed, in our feature space, unknown samples are located far away from class centers, so to recognize them we just have to measure their distance from the nearest center and then compare it with a threshold. So let's visualize how our model works. At the beginning, we train it on an initial set of classes that will form compact clusters in the feature space. In a later evaluation phase, the model faces both new known samples, highlighted here in green, and never seen ones that we see in red. So by looking at how they are positioned in the feature space, the model is able to correctly distinguish them. Now, a new training episode begins, and some of the unknown samples become a new class in our feature space, which automatically adapts itself to make room for new class clusters. During the second evaluation phase, the samples belonging to recently learned classes are now recognized as known, while unknown ones are still correctly detected. All of this can be repeated a number of times, with new classes being learned in each episode. Let's look at some experimental results. In the rod to arid shift, we train on real pixels collected in lab settings, with well-illuminated objects laying on a table. The target visual domain still contains real pixels, but in its case, the light conditions may vary and some objects also show occlusions. Given that our proposed approach is the first one designed to tackle all the challenges of our task, our competitors are obtained by integrating open-world methods with domain generalization ones. We consider three different performance metrics. The first measures the ability to recognize known objects without applying the unknown rejection policy. The second instead measures the accuracy on known objects when the rejection policy is applied. But the most important metric is the third, which considers both the accuracy on known objects and the accuracy on unknown ones. In a second benchmark evaluation, we still adopt arid as our target domain, but train on a synthetic version of rod. Even if this case is more difficult, our performance is on par with the previous case, and we are the first to obtain this result. The last benchmark is inspired by our exemplary application, with training source samples being handheld by a human, and target test samples being naturally positioned in a home environment. As you can see, in all cases, our contrastive open-world method outperforms the competitors. In conclusion, I have presented to you our solution for cross-domain open-world recognition. If you are interested, you can find our code online and replicate all our experiments.